In this video, we're going to prove the result that we conjectured in the last video, which is that the orbit and stabilizer of a given set element under a group action are related to the order of the group acting on the set. All right, rather than say all that out loud, let's write that down. Okay, so let's say we have a G group acting on X. Here's the theorem. If G is finite, and X is any element of our set, the set being acted on, then the size of the orbit of X times the size of the stabilizer of X, and we'll just assume that all stabilizers are in G this time, that product is equal to the order of the group G. And in this video, we're going to prove it. For the proof, we're going to use a fact that we've proven previously. Here's that fact. If G is a finite group and H is a subgroup of G, so if G is finite and H is a subgroup of G, then the index of H and G, that is the number of cosets of H and G, times the order of the subgroup is equal to the order of the entire group. That was part of proving Lagrange's theorem. So the key to our proof is that we're going to show that this H is the stabilizer of X. That is, we can think of the stabilizer of an element of our set as this subgroup. All right, there's no secret to that because we know that the stabilizer is a subgroup. So we're actually just going to call that H. We're going to define H to be the stabilizer of X. We will also show that the number of cosets of H in G has something to do with the orbit of X. Now, we can't say that each element of the orbit of X is a coset of H and G because orbits don't necessarily even consist of group elements, but we are going to find a correspondence between those. And of course, we have G over here on the right. So that's going to be the approach, but let's jump into it. All right, let's start by assuming the hypothesis. Assume that G is finite. And let's assume that X belongs to the set being acted on. We're assuming also that we have an action of G on H. All right, so we assume all of that, and we're going to define H to be the stabilizer of X in G. All right, so we're going to prove the following fact, and once we prove this, the rest of the proof is really just using this known fact here, using Lagrange's theorem. All right, so the thing we're going to claim here is that each of H acts on X to produce a different element of the orbit of X. Okay, so here's what I mean by that. If I have H and I have all of the cosets of H listed out, and because G is finite, therefore H has to be finite, therefore there have to be a finite number of left cosets. So let's say I list all of those out. Let's assume the left cosets of H are A1, H, A2, H, and so on up to, let's call it AK, H. So I'm going to make two subclaims here. Okay, I don't think I will have subclaims, but I do have two subclaims that I think I need to prove. Okay, first of all, every element of AIH for any fixed I, every element of that coset sends X to the same element of the orbit. I mean, we know that whatever these elements, whatever these group elements send X to is going to be part of the orbit of X, because that's what it means to be part of the orbit of X, is if I can act on X with some group element and get Y, then that means that Y is part of the orbit of X. Okay, so I'm claiming that every element of this coset is going to send x to the same y. More on that in just a bit. The other claim, or the other subclaim that I will try to prove, is that if I is not equal to j, then AIH and AJH send x to different elements of the orbit. Okay, let me just say a little bit about why I'm motivated to try to prove these two subclaims. If I could prove both of those things, then here's what I'd know. First of all, I know that everything that is in the orbit of x has to be the result of acting on x with some group element. That group element has to belong to some coset. Okay, so when I look at all of these cosets and their actions on x, I know that that's going to give me all of the orbit of x. In other words, if I look at all of these group elements acting on x, then the results of all those group actions will make up the entire orbit of x. I'm not going to miss anything in the orbit of x by looking at the problem this way. I also know, if I can prove these two subclaims, that each of these cosets, this one, all the way up to this one, each of these cosets is going to send x to a different element of the orbit. One of them, by the way, is going to send x directly to itself. X is part of the orbit, and whichever one of these cosets is just h, that is the identity coset, that's going to be the one that sends x to x. But each of the other cosets will send x to a different element. So if I want to count elements in the orbit of x, all that I really need to do is count cosets. That's why we have this situation where I can map the objects in this equation, which we have proven, to the objects in this equation, which we want to prove. So again, we're saying that h is the stabilizer of x. Of course, the order of g is just the order of g. We're going to prove that the number of left cosets of h is the same as the number of elements in the orbit of x. All right, so that's the claim. Those are the subclaims. And now I think the only thing left is to just do the work. So let's get the proof going here. So we're going to prove the two subclaims, because I think those two subclaims, if proven, will prove this claim here. Because the claim is really just saying that different left cosets map x to different elements. All right, so let's get started. Proof of subclaim 1. All right, so let's fix an I so that we're fixing a coset. Some I in the set 1 through k. Fix a left coset. And let's suppose that AIH and AIH prime are two elements, any two elements of AIH, that coset. We will show that AIH dot x is the same as AIH prime dot x. That will show that any two different elements of this coset are going to map x to the same thing, because the results of these actions are equal. All right, so to show that, we're just going to make an observation. AIH acting on x, that's the same thing, just by the rules of how group actions work, as AI acting on the result of h acting on x. And the result of h acting on x is just, well, that's just x, because h is part of the stabilizer of x. So that's AI acting on x. And I don't know what that's going to be, but I don't think I need to know, because now I'm going to say, well, what happens if AIH prime acts on x? Well, then I get the same thing as AI acting on h prime acting on x. And, well, again, h prime belongs to the stabilizer, so that's just AI acting on x. So these two are the same. So AI h acting on x is the same as AI h prime acting on x. And because these were any two elements of the coset, because AIH and AIH prime represent any two elements of AIH, every element of AIH, that coset, moves x to the same thing. Not necessarily x, but the same thing nonetheless. So that's subclaim 1, and that's proven. Now let's darken our color a little bit, just so that we can have a little bit of a distinction here, and we'll prove subclaim number 2. Oops. So this is the proof of subclaim 2. And now we want to show that elements of different cosets, different left cosets, map x to different things. All right, so suppose I and j both belong to the set 1 through k, and I is not equal to j. And then we'll show that AI, H, and AJ, H act differently on X. In other words, they act on X to produce different elements. So that's what we will show. Okay, well, first of all, I'm going to do a little useful recasting of this problem because I never know what to do with the fact that I does not equal J. And it's also kind of hard sometimes to show that AIH and AJH, that those actions on X are not equal. It's just hard to show that things are not equal sometimes. So instead, I'm going to recast the problem so I get to assume things are equal and then prove that two other things are equal. The way I'll do that is I'm going to prove the contrapositive. Contrapositive. If AIH and AJH act the same on X, the same, then I equals J. Okay, so let's assume AIH and AJH act the same on X. All right, enough preface. Let's get to it, shall we? If those two cosets act the same on H, one thing we just proved is that this entire coset acts on X with one voice. In other words, I can pick any element here, and I'll get the same result acting on X. And I can pick any element of this coset, and I'll get the same result acting on X. And because I'm assuming that these two act the same on X, then those two elements will have the same action on X between each other. So rather than deal with just an arbitrary element of AIH and AJH, I'm going to use the most obvious one. We know AI belongs to AIH and AJ belongs to AJH. That's because I can write AI as AI times the identity. The identity is an element of H. AJ is equal to AJ times the identity. Identity is an element of H. So those belong to their respective cosets. And by our assumption, since we're assuming these cosets act the same on X, AI.x equals AJ.x. Okay, now here we're going to do a little magic trick here. We're going to turn that into somewhat more useful information. I know that AI.x is the same as AJ.x. I'm going to act on each side with the inverse of AI. So act on each side with the inverse of AI. That should still give me the same result because I'm just acting on the same set element with the same group elements. But now I can use my group action rules and say, well, that composition of actions is the same as if I compose the group elements. So there I get that, and then there I get this. Now this is turning really nice. I mean, this is, you may have noticed by now about halfway into the course that this is a very common thing that we do with just anything group related, is try and get things back to an identity, try and hit things with an inverse and see if that simplifies the problem. That's kind of what we did when we were proving that that a homomorphism is one-to-one if and only if its kernel is trivial. Same strategy, turn things into the identity and good things will happen. So now we have the identity acting on X. That's the same as AI inverse AJ acting on X. But the identity acting on X is just X. So really what I've come up with here is that the AI inverse times AJ, that's a times, not an acting on X is just X. Well, wait, what does this mean? If AI inverse AJ acts on X and produces X, that means AI inverse AJ belongs to the stabilizer because it acts on X and produces X. Well, that's great, but then that means that AI inverse AJ is equal to H for some H in my group. And that means if I multiply both sides on the left by AI, AJ is equal to AI H. But wait, what does that mean? If AJ is equal to AI times an element of H, that means AJ belongs to AI H, belongs to that coset. But wait a minute, AJ also belongs to AJH, because each element belongs to its own coset. So these two have something in common. They both have AJ. And one thing we know is if two cosets have something in common, that means they intersect. They're not disjoint. That means they are the same coset exactly. They're the same coset, and I assume that A1H, A2H, that all the way through AKH, those were all the different cosets of H. So that means that I has to equal J, because I assumed that all of those were different cosets at the beginning. So that means we've proven that I equals J, because we've proven that AIH and AJH, if they act the same on X, that means they must have something in common. So we've proven that I equals J, and therefore different cosets of the stabilizer, different cosets send X to different things, different elements of the orbit. Okay, so let's zoom way out because a lot has happened here in these almost 20 minutes. But here's the summary. So what we proved is that every left coset of H, and I really should have said here the different left cosets. I didn't emphasize that enough. I think that that's usually implied, but I really should have said that at the start. Assume that the different left cosets are these. There's K of them, right? Well, now we know that each of these cosets sends X to a different element of the orbit. And every element of the orbit is represented by one of these cosets, because if it's in the orbit, somebody has to send X to it, and that somebody has to belong to a coset. So here's the wrap-up of the argument. The cosets, left cosets of H are in one-to-one correspondence with the orbit of X, that is, with elements of the orbit of X. So that means that the number of cosets, which is, again, the index of H and G, that number of cosets is equal to the number of elements in the orbit of X. The number of elements in H is the same as the number of elements in the stabilizer of X because, well, that's what H was. And because the product of the index and the subgroup order is the group order, that means that the product of the orbits, or the order of the orbits, and the order of the stabilizer has to be the order of the group. That's just a wonderful finding. That agrees with what we found in the previous video where we had U15 acting on Z15, where we had like all these 4s and 2s and 8s and 1s, but the order of the orbit and the order of the stabilizer always multiplied to 8, which was the order of U15. Now we've proven that that happens in general, and we'll see some applications in class.